Okay, just to reiterate, we're going to first go over the physics of the diffraction gratings as the groundwork, just so we all understand how these devices work. Then we'll kind of have a discussion about what the computational details are. Then we'll go into the actual Python script for setting up this calculation, and then I'll show you at the very end the output from running these the Python script. Okay, so let's get started. Diffraction grating is, in principle, a very simple device. Okay, so what it is it consists of, as you can see here in the schematic, some periodic modulation of your structure, and then you hit that structure with some incident plane wave, which is shown at the bottom here. Okay, and this generates these diffraction orders at very specific angles, as you can see, and they're labeled by the diffraction order, which is an integer. Okay, we'll discuss this in more detail. These structures are typically made of glass. Okay, so it's a transparent material. It doesn't act as an absorber. The light propagates through. They're widely used in many different applications. So think spectrometers, okay, which are used for a lot of metrology applications. They're also used as part of near-eye displays for augmented reality. And they're being heavily kind of researched for a lot of useful applications, as I mentioned. So typically, the way these devices have been modeled is if the period of these gratings, which is denoted by this capital lambda here, is many times larger than the actual wavelength of the incident light, you actually don't need to do any full wave simulation. You can actually solve this using what's known as a scalar diffraction theory. Okay, and there's a very well-known book by Joseph Goodman, former professor at Stanford, that goes over the theoretical details of how to do that calculation. Okay. However, when you shrink the dimensions of the grating down to the length scale that's comparable to the wavelength of the light, then you start introducing polarization dependent effects. Okay, and that's when you do need to use some kind of a full wave Maxwell solver like FTTD, and there are others like RCWA, and I'll talk about the trade-offs of why you'd want to use one method versus the other in just a second. Okay, so again, structures with a periodic modulation of the refractive index that's being hit with some incident plane wave source. That incident plane wave source is then diffracted or scattered, and it generates these finite numbers of diffraction orders, both in transmission and in reflections. Okay. Now, there are two main types of gratings. This schematic is showing you just one of them. It's known as a surface relief grating. That's where the structure, as I mentioned, is being modulated. But you can also modulate the refractive index, okay, using a photopolymer, okay, using interference lithography, for example, where you have two incident laser beams. They generate some standing wave pattern, and that standing wave pattern imprints some refractive index modulation, okay? That also gives rise to the same effect. And they have different use cases, a surface relief grating versus a holographic photopolymer that we won't go into in this tutorial. When you're designing these structures, the key is the unit cell. Okay, so these are assumed to be a perfectly periodic structure. And so we can design their properties just by designing the unit cell. And for the case of a surface relief grating, there are many different kinds of unit cells. So I show you three of them. We're going to just focus on one today. So the one I'm showing you here is a binary grating. The binary refers to the fact there are two heights, okay? Two different heights that we can modulate. And the degrees of freedom in this unit cell are the height, obviously, but also the fill factor, the width of that grating, and the periodicity, this lambda, that controls the actual locations of the diffraction orders, okay? So once you fix lambda, capital lambda, you fix where you find those diffraction orders. And the design of the unit cell, all that does is concentrate the light into those various orders, okay? And so that's where the design element comes in. The binary grating, as you can see, it's a symmetric structure, right? There's a mirror symmetry that goes right through the middle of that structure. And because of that, the diffraction orders are symmetric. So the minus orders are equivalent to the plus orders, okay? But you can introduce an asymmetric unit cell. And there are two types here. There's a blazed or a slanted grating. And those structures preferentially send the light in one direction versus the other. And this is actually very useful, right? So suppose you want to design a structure where you're concentrating the input light into a specific direction. And so in that case, you would want to use an asymmetric grating. And they have different degrees of freedom. What's really exciting, I think, as you'll hear in the presentations this afternoon, is taking these structures and applying tools like inverse design, okay, which takes these simple primitive structures that have been looked at and investigated quite heavily, but then extends the design capabilities in very interesting directions by parameterizing the entire surface of the gratings, okay, and using gradient-based optimization. That's not something we're going to get into in this talk, but I just kind of hopefully this will pique your interest into kind of investigating how to take these calculations that I'm going to be showing you today and being able to extend them using inverse design for new kinds of devices. The operating principle here is quite simple, okay? And so, like I said, we send in an incident plane wave. It has some that incident plane wave. Let's assume it has some wavelength, like little lambda. The finite numbers of diffraction orders that this grating generates can all be calculated using this very simple equation. Okay, so look carefully at the axis orientation. So the plane wave is propagating along x, okay, and the periodic direction is in y, okay. And because of the translational symmetry in the y direction, this means that you can the incident plane wave, the ky is conserved up to these factors of 2 pi over lambda times some integer, okay. And the way you can compute the diffraction orders is you can, for every single integer m that generates some real kx, that means it's a propagating mode, okay, you have a diffraction order, okay? And if m becomes large enough, kx becomes imaginary, and therefore you have no power. There's no more diffraction orders, okay? So this equation sets an upper bound on the number of diffraction orders you have. And as you can see, it entirely depends on the refractive index of the medium that you're propagating or reflecting into, as well as the periodicity of the grating structure, okay? So using just those two physical parameters, you can then compute how many diffraction orders a given structure will have. That's why I said that once you fix lambda, you fix the location, the position of these diffraction orders, and then the design is that what that leaves you with is how to concentrate the power into a given design, into a given order for whatever your application is, okay? And as an example, suppose I have an incident plane wave that is at a half a micron with a structure that has a periodicity of 10 microns, and I want to look at the transmitted orders into air, okay? And I'm coming in with a normally incident plane wave. For this structure, I have 20 diffraction orders, okay? Not any more than that. Okay, now let's switch to the actual computational details of how you actually design these structures. Okay, so here is a unit cell layout that we'll be looking at shortly in the code. So what we have here is it's very similar to what I've shown you in this slide. We have the grating itself, which has a height, some height, okay? The period of the unit cell is shown in the y direction. That's also labeled by this GP parameter. There are PMLs in the x direction, in the propagation direction, and the cell is periodic in the y direction, as I mentioned. The source, the incident source that we're going to be using here actually is incident from within the actual glass material, which is denoted by this red line. And what we're going to do is we're going to compute the transmitted orders by placing a monitor in air just outside of the grating, okay, as you can see here, labeled by this line, okay? And we're actually also going to compute the reflected order. So this grating generates both the transmitted orders into air, but it also generates reflected orders back into the glass, okay? And we're going to compute both of them, and we're going to verify one key property that this grating must fulfill, which is the sum of the power in all of the transmitted and the reflected orders, okay, that must sum to 1. Okay, the reflectance, the sum of the reflectance plus the sum of the transmittance of the transmitted orders, that all must sum to 1, obviously because of energy conservation, okay? So that's always a way to validate these calculations, and I'm going to show you how we set this up in the code, right? It's just to make sure you've accounted for every single order correctly, and you've computed the reflectance or the transmittance correctly. The figure on the right shows you a far field transmittance diagram of what the actual transmitted orders look like in air as a function of the angle and the wavelength, okay? I'm not going to do this kind of calculation in this tutorial, but this involves a near to far field transformation, which Meep supports, okay? So in this case, you would run your simulation, you would compute the near fields, and then you would take those near fields and propagate them into the far fields, and you would end up with something that looks like this, okay? And the nice thing about this is a single calculation. It gives you the entire broad bandwidth response. You can see it extends from 400 nanometers to 600 nanometers. And it shows you exactly where those finite set of transmitted orders lie, okay? So in this case, you could see it, these lines, these streaks, right? So this would be the m is equal to +1, +2, -3, and so on. I'm not showing you the minus angles because this is symmetric, as I mentioned, right? So everything here also is mirrored in the bottom of this curve. But you can clearly see that in this example, most of the power of the incident light is channeled into the first order, okay? Because I haven't shown you the color bar here, but the color denotes the strength, the intensity of the fields. The darker it is, the more intense it is. And you can see here, most of the intensity ends up in the first order, okay? All right, so this calculation, there's really 3 key things you need to know, okay, when you're setting up these calculations that we're going to review as part of this tutorial. The first is, how do you generate a broadband oblique source? Okay, so as I mentioned, the incident source here is a plane wave, okay, and typically in the simplest case, that plane wave is incident at normal incidence. But suppose you want it to come in at an off normal angle, okay? And you want it to also compute a broadband response, okay? That requires a little bit more care because the way to analyze the results, okay, as you will see, is you cannot just assume that because you're coming at this off normal angle, every frequency in that pulse also is coming in at that same angle. It's actually a little bit different, okay, and I'll show you why in a second. The second detail that we'll be looking at is how do we actually compute these reflected or transmitted orders, okay? So this involves a concept known as mode decomposition, okay? I have an incident plane wave. It generates some scattered field, but that scattered field I need to decompose into how much power resides into individual plane waves that are going off at discrete angles, right? So I need some way to decompose that signal into these finite set of diffraction orders and then compute how much power there is in that signal in each of those orders, okay, both in reflection and in transmittance, okay? I'm going to show you an example of that as well. The last thing is, that we'll look at is, this is a very simple one-dimensional grating, but suppose I extend this concept to a two-dimensional grating, okay? So something that looks like, as I'll show you here, that looks like this, okay? It's not just a 1D grating, it's a two-dimensional array. It's not a simple square lattice, it's a triangular lattice. Okay, so I want to be able to model a triangular lattice, for example, of these these circular rods. How do I do that using Meep, which only supports a rectangular lattice? Okay, so there's some additional things we'll have to think about in that case, involving supercells and how to interpret the modes of a supercell using a rectangular lattice when we're trying to model a triangular lattice. But for the beginning, I just want to focus on the 1D design, and then at the very end, we'll switch to a 2D triangular design. Okay, so let's first talk about broadband oblique sources. Okay, so let me first define what I mean by an off-normal angle. So this is my unit cell. The plane wave is incident along the x direction. And what I'm calling as the normal incidence, or 0 degree, is the plane wave that's propagating along the x direction, okay? So that's what I'm calling 0 degrees. Anything that's greater than 0 degrees, you can assume that it has this counterclockwise rotation around the z-axis, okay? That gives you this orientation. So the wave vector of the incident plane wave is oriented in this, using this convention, okay? And so what this means is, if you're propagating in homogeneous media, you all know what the dispersion relation for a plane wave in homogeneous media is, right? You can solve that using Maxwell's equations. You get this formula, so a relationship between the frequency and the wave vector, okay? In Meep, as you know, the speed of light is equal to 1. We set that for convenience. And because of this, you can then generate a formula for the wave vector that depends on the index that you're propagating in, the frequency of the source, as well as the angle of the incident plane wave, okay? But there's a problem here, if you can spot it, which is this equation only applies for a single frequency, okay? So once I specify what my block periodic boundary conditions are, I do so for a fixed k. But suppose I have a pulsed source, which has multiple frequencies, right? That then means that those other frequencies, okay, if I'm propagating at some off normal angle, okay, for any frequency that's, say, not the center frequency, the frequency that I've specified the block periodic boundary conditions for, the angles that are incident, those are not the same as theta. In fact, they're given by this formula here, okay? So this is something that we'll need to be very careful about. Okay, so when we're doing these broadband calculations in Meep, or in FTTD, okay, Numerical has this issue as well. If you're coming in at some off-normal angle, the way you interpret the results depends on the frequency of the incident source, okay? And each frequency has a different incident angle, and you can calculate that using this equation that's shown here. Now, I think Numerical has a special feature called BFAST, where they support boundary conditions that can enable a broad bandwidth response at the same frequency. But from what I know, it has some limitations around stability and in use cases. And there's some work, very preliminary work, some discussions that we had to support something similar in Meep that we can talk about in the Q&A for those who are interested. But for now, let's assume that once you specify the block periodic boundary conditions, this k, you do so for a single frequency. And so if you have a broad bandwidth pulse and you're looking at a broadband spectral response, you need to interpret the incident angles using this formula. Okay, so that's point number 1 to be aware of. And we'll look at an example in code in a second. The second thing to be aware of is mode decomposition. Okay, so the issue is, we have this unit cell calculation. We have our source, okay, at whatever angle we're going to specify. We do our time stepping. We then monitor the fields at these DFT monitors. And then in post-processing, what we need to do is to decompose these Fourier transform fields into the basis plane waves and to compute how much power there is in each of those plane waves, right? Both in transmission and reflection, as I said. And so, and when we're computing diffraction efficiencies is essentially equivalent to the power in the actual diffraction order normalized by the power in the input source. Okay, so we need to compute the power in the input source, we actually need to do a separate simulation where we just have the homogeneous media and the source to compute the input power. And then we do our real simulation. So this is something that is kind of a general thing in Meep. When you're computing these kind of normalized quantities, you always need to do these reference calculations with just the source in the source medium to compute the input power. And then you do the actual simulation, in this case with the grating, to compute the power from your structure, and then you divide the two to get a normalized quantity. But in this case, the diffraction efficiency, we need to compute the power in these given orders, okay? The order itself, the diffraction order, is specified by 2 things. So one is this integer m, okay, which I already told you about, which is this quantity here. It tells you the actual angle, okay, of the actual diffraction order. But the other thing we need to know is the polarization. Okay, so this is really important as well, because as I said, in these cases, the period of the grating is comparable or smaller than the wavelength of the incident light. And so you have polarization effects, wave effects that you need to model. And so when we're doing the mode decomposition, you also need to specify what the polarization of the diffraction order is in order to do the actual decomposition. Okay, the way we do this in Meep is we use what's called a mode decomposition, which is used to compute a complex mode coefficient. Okay, and the square of that mode coefficient gives you the power in that mode. Okay, there's a link here that this presentation will be shared with you all afterwards that you can go read about the theoretical details of how mode decomposition works. It's essentially equivalent to a scattering matrix or scattering parameter that we were talking about in the previous talk. It's a complex quantity. The imaginary part describes the relative phase of the mode relative to that of the source. But the squared magnitude of the complex mode coefficient gives you the actual power in that mode. Okay, so it's kind of Meep takes care of this for you under the hood. Okay, so all you do, as I'll show you, in the API, you specify the mode, you give it an M, you give it the polarization, and then under the hood, Meep will compute the mode coefficient using this overlap integral and give back to you the result, which you then compute the squared magnitude of to get the power. Okay, so it's relatively straightforward calculation. Now here's the important part. For these kinds of calculations, okay, we're interested in plane waves, right? So we're propagating in air or in our substrate. And Meep has this built-in feature known as a diffracted plane wave object that we actually kind of recently added that is described in some detail. As you can see here, this is the page from the user manual, okay? So there's a diffractive plane wave object. This is an object that you pass to get eigenmode coefficients, which is the actual mode decomposition routine. And as I mentioned, you need to specify what the diffracted order is. In this case, this is a set of 3 integers. For a 1D grating, it's just a single integer. You specify what the plane of incidence of your grating is. And then from that, you can specify the polarization, whether it's S or the P. S for the case of the electric field being perpendicular to the plane of incidence, and P for the case of parallel. Okay, so this diffracted plane wave object is the API that you use to specify the plane wave that you're interested in. You pass this to the get eigenmode coefficients, and then Meep will compute that complex mode coefficient, which you square. And then you normalize it, you divide it by the input power to get the actual diffraction efficiency. I'm going to show you how this all works in a second. Okay. Okay, so let's go back here. So that's really it. These are the key kind of details for how you set up these calculations. So let me just do one more review before we turn to the code. Okay, so we have a one-dimensional grating. Because it's a periodic structure, we're going to only model a unit cell of this grating. We have PMLs in the X direction, block periodic in the Y direction. We have our sources. We have our DFT monitors. Okay. The challenges mainly are, as I mentioned, how do you set up a broadband oblique source? How do you do the mode decomposition? So now let's actually look at a practical example of how this all works by turning to an actual Meep script. Okay, I'm just going to kind of go through this with you all line by line. Okay, you can all see this here. Let's see if I can make this zoom in a little bit here. Okay, I've actually set up this specific script as a form of a unit test. And the test, as you'll see, this involves what I described earlier. So we have a grating. We're going to compute all of its reflected orders. We're going to compute all of its transmitted orders. And we're going to verify that the sum of the reflectance and transmittance is equal to 1. Okay, So that is a way to validate that you've computed, you've set up this calculation correctly, and you've properly accounted for all of your diffraction orders. Okay. All right, so let's kind of go through this. So to set up this actual structure, that's relatively straightforward. We only have a handful of parameters here. So we have our PML thickness, our substrate thickness. There's a padding, okay, so an air padding between where our grating ends and where our PML begins. Okay. If I switch back, so this is the actual structure. So these are the parameters in the script are shown here in this schematic. Okay. We have the height of our grating. These numbers I just chose arbitrarily. So the periodicity is 6 microns. The height of the grating is ½ a micron. The duty cycle is 0.5. We compute what the dimensions of the unit cell are, both in the x direction, Sx and Sy. And a 1D grating is a 2-dimensional simulation. And we'll talk next about a 2D grating, which is a 3-dimensional simulation. We have PMLs in one direction, just in the x direction, as I mentioned. We're going to excite the grating using a pulse source that has a center frequency of ½ a micron. Okay, so here's how we specify that. The wavelength, the center frequency is ½ a micron. The substrate is a glass material with an index of 1.5. And to build the actual geometry, we basically just need 2 block objects. So one block to describe the substrate, and then another block to describe the grating. Okay, that's all there is to it. So one block to describe the substrate here, and then adjacent to it is the actual grating material. So this, these are the details of the actual structure and the sources. Now I have a function that will actually compute what the reflected and transmitted orders are. And it's set up to actually, there's a single parameter to this function, which is the angle of the incident source. And we're going to do this test for both a normally incident source, but also an off normal incident. This time, the angle is 10.7 degrees, just some arbitrary value, okay? Just to demonstrate to you how this works in these 2 cases, okay? One of the nice things about this structure is that if you're coming in at normal incidence, you can actually use mirror symmetries, right? So there's a mirror symmetry plane that's it's in the normal direction is in the x direction, okay? That goes right through, that you can use to reduce the computational size by a factor of 2, okay? This isn't so important for a 2D calculation unit cell like this, but it can be important for a 3D calculation, particularly when you're increasing the resolution as part of a convergence check. Okay, so whenever you can, you should try to exploit these things because it will help you to get better and faster runtimes and use less memory. Okay, so we first check that if we have a normally incident source, we use a mirror symmetry plane in the y direction. And if we are coming at an off normal incidence, we don't have any symmetry. So unfortunately, we cannot exploit that. So this is just left empty. K describes the actual block periodic or periodic boundary conditions. If we're coming in at normal incidence, we actually have a wave vector of 0. If we're coming in at off normal incidence, what we're doing is we initially start with a wave vector that's along x, and then we just rotate it, right? So just like I described to you here, if you recall. Okay, so if we want to define what the k vector is, okay, we already know what its magnitude is, right? The magnitude is n times omega. N refers to the source medium, which is in this case is this glass material. The frequency is the center frequency of the pulse, okay? And then we rotate it, or we modify it such that it corresponds to this actual angle, okay? And so there's actually a built-in routine in Meep called rotate that given a vector, you can rotate objects around it. So in this case, we're going to be rotating around the z-axis by some theta in degrees, okay? And theta in is basically just the theta, which is a parameter in degrees, converted into radians, okay? Now to actually set up the source, we're going to use the source is going to have an amplitude function. So our source, this source here, is going to have this e to the I k ky times y k dependence, okay, to generate the actual plane wave. And the K is what the K that we use up here, which is also going to be the K of the block periodic boundary conditions. And the source is going to be polarized to have electric field out of the plane, so in the Z direction. So this actually corresponds to the S polarization. And this is something that we're going to get back to when we talk about the mode decomposition. The polarization, in this case, it's very simple. The polarization of the source and the polarization of the diffracted orders are the same, right? So if you're coming in with an S polarized source, the diffraction orders are also going to have the same polarization. But if you have a 2D grating, that's not the case. Okay, if you have a 2D grating, if I come in with some linearly polarized source, the diffracted orders are going to be both polarization S and the P. Okay, but in 1D, things are a little bit simpler. Okay, once we've set up the source, and this is, by the way, this is fairly standard stuff that's reviewed in the Meep tutorials, how to actually set up these sources. So for those who've set up these calculations before, this should be fairly similar. Okay, so what we're going to do is we're going to do a reference calculation where we compute the power from just the source. Okay, so we set up our simulation object. Note here, there's no geometry. We're just going to set the default material.
You didn't share this window. Sorry, share the slides. You're only sharing one tab.
Okay, just a second. Okay, I think everyone should see that. Sorry, I thought they would switch automatically. I guess it doesn't. Okay, so I've been going through over this script just to go over it briefly just to get caught up. So this is a very simple script that describes this 1D Bray grating that we've been looking at. These are the geometric parameters from the schematic, for example, the PML thickness, the period of the grating, the height of the grating, the duty cycle. We then set up the actual geometry. It consists of 2 block objects that I mentioned. And then I have a function that, given the angle of the incident source, will compute the reflected and transmitted orders, okay, which I'll get to in a second. Okay, but before we get to the grating calculation, we have to do a reference calculation where we compute the power in just the from the source. Okay, and so the very first calculation we do is we define a simulation object with just the default material that's glass everywhere, with our source, with our power monitor. We do the time stepping. We compute what is the power generated by just the source, because we're going to need this when we normalize by the power from the grating to get a normalized diffraction efficiency quantity. Okay. I then set up my reflection monitor. Okay, so this is adjacent to the source. It's inside the actual glass material. I do the time stepping. I then, at the end of the time stepping, save the flux from this calculation. Okay, and so I do it in 2 different ways. One is I actually save the flux values. Okay, and these are going to be used for the diffraction efficiency. But I also store the data because I need to when I do the grating calculation, I need to subtract out the Fourier transform fields when we do the real run, because we don't want to have the incident source field be part of the Fourier transform reflected fields. Okay, we reset Meep. We now do the actual grating calculation. So now you see here we have a grating object. Okay, this consists of the actual grating structure. We set up our mode monitor. So one is for the reflected fields. As I mentioned, this is in the glass material adjacent to the source. We do a load minus flux to subtract out the fields from the source. Again, this is a very common procedure in Meep where for reflected fields only, we want to remove the incident fields from the source. We then add a transmitted field monitor, okay, which is in the air. We do our time stepping. And now is when we do our actual mode decomposition. Okay, so now we have the fields stored from doing the time stepping of the gradient calculation. Now we want to do the actual mode decomposition using Meep's built-in mode decomposition tools. So to do that, we first need to compute what are the actual orders that we have in our calculation, right? So the set of integers that define the transmitted and reflected orders. And to do that, we need to compute it kind of manually using that grating equation that I showed you before. So it depends on things like the center frequency, in this case, if we're looking at reflected orders, we need to know it's the actual index of the reflected modes, which is the glass, okay, and also the period of the grating, okay. So once we have a set of diffraction orders, a set of integers, okay, we have a loop that one by one, it calls this get eigenmode coefficients routine and computes first the reflectance values of the reflected orders, okay. So it calls get eigenmode coefficients. This is the fields from the DFT monitor. It specifies the actual mode that you want to decompose. So in this case, this specifies the diffraction order. This is an axis quantity, if you recall from the diffracted plane wave documentation that's used to define the plane of incidence. 1 is for the S polarization, 0 is for the P. Okay, so we're interested in the S polarization because we have a S polarized source. And then from this complex mode coefficient, okay, we compute the power, okay, or the reflectance, which is essentially the squared magnitude, just like what I said earlier, of the complex mode coefficient normalized by the input source, okay? And then we'll print it out just so we can actually see what those values are. And then we're going to keep a running tally of the sum of the total reflectance, okay? And if we're coming in at normal incidence, we're only going to compute only the positive orders, okay? Which means we'll need to multiply the reflectance by 2 because we're not going to compute the negative orders. And if we're going to come in at an off-normal incidence, we need to compute for every single order and add those results one by one. Okay, that's why there's this kind of if clause here to account for the special case if we have a normally incident source, okay, and we're looking at the non-zero diffraction orders. In that case, we need to double them because we're going to have from the plus side and the minus side. Okay. The same process that we just did for the reflected orders, we're going to do for the transmitted orders in air. Okay. So note, to compute the reflected orders, we need to. This is very important, okay? We need to look at the medium of the reflected orders. In this case, it's glass. Here, the transmitted orders are in air, okay? So we're going to compute the M plus and the M minus terms. And then again, we have this loop that's going to go one by one through all of the transmitted orders, compute its mode coefficient. From the mode coefficient, form the actual diffraction efficiency, and then keep a running tally in T sum of the total transmittance of the transmitted orders, okay? All right, that's it, essentially. That's really it for the calculation. And then at the very end, we're going to compute from the DFT monitors what the total flux is, okay, using these built-in routines. And we're going to compare the tallies, the reflected and transmitted tallies, to the total Poynting flux. And they should be the same if we set up this calculation correctly, okay? And that's actually the check here. So these assert statements verify that the tallies from the mode decomposition are equivalent to the total Poynting flux for the reflected and transmitted modes. And also that the sum is equal to 1, okay? To make sure that energy is conserved, that we've accounted for all possible diffraction orders, okay? So now we'll go and run this calculation. I've already run it for you. I'm just going to show you the output. Okay, so the output of running that script is here. So we're going to do 2 cases, one in which we have a normally incident source, so theta is equal to 0. And then the second one where the theta is off normal is at 10.7 degrees. So the first output that you see here, that's for the normally incident source, okay? So the first thing that happens is this part is this initial reference calculation where we have just a homogeneous material, we compute the total power. And then we do the actual calculation where we have these 2 block objects that describe the grating. We do the time stepping. At the end of the time stepping, we have these 2 loops to compute the reflected orders, both in reflection and transmittance. And you can see here the output. Okay, so in this case, the M is equal to 0 order has about 3.6% of the total power. And then this shows you for +1, +3, and so on, all the way up until the largest possible. And then it switches to the transmitted orders, okay? And then the key result is shown here at the kind of the end. Let me see if I can zoom this a bit, might be small to see. Okay, so these lines show you the actual values for each of the diffraction orders separately. Okay, so this is the m is equal to 17, for example. This has a very tiny amount of power in it. And then the very end of the run, you can see a side-by-side comparison. So the first column, this value is the tally of all the reflectance from the individual modes. And then this second column is the total pointing flux of the reflected modes. And you can see how close they are, right? So they agree to at least, you can say like 2 decimal places here. So there's about 5.7% of the total input is being reflected and about 94% being transmitted. And then the sums should be roughly 1, which they are in this case, okay? So that's for the normally incident run. What about the run at 10.7 degrees? Same thing, okay? We do a reference calculation with no structure, and then we do our actual calculation with the structure and the same kind of outputs, but now we show you the actual negative because it's not symmetric anymore, so we have to compute the negative orders manually. So you can see here, this is the m is equal to -21, -20, and so on. And these values show you the actual reflectance values. And then here are the results from the transmitted orders. Okay, 1 by 1. And then at the very end, you can see the totals, okay? And again, they agree fairly well. And the thing to verify, obviously, is to keep doubling the resolution, okay? So the more you increase the resolution, in principle, the better the agreement should be. And that's another way to validate your results as well, right? So this resolution that I chose for this run was, I think, about 100 pixels per micron. You can see here, it's printed up here. Okay, it's just a 2D. This is fairly fast. So I ran this with 4 processes. It ran in 100 seconds. Okay, 2 different calculations at a fairly modest resolution. Okay, let me stop and take some questions first about the 1D grating, and then we'll switch over to the 2D triangular lattice. Any questions?
Normal incidents where you use the mirror symmetry and then only computed the positive diffraction orders and then doubled your results, wouldn't that mean you compute the 0 order diffraction twice?
That's a good question. The answer is yes. The question was, in the way that we had set it up, let me just do full screen here. In the way that I had set up the actual calculation of the diffracted orders, so for the case where you're coming in at normal incidence, right? The way I was doing that tally is for the diffraction orders that were not 0, right? I was doubling the values because I didn't want to compute the negative quantities because they're symmetric. But what about the mode that's coming in, the m is equal to 0 order, okay? That order you don't need to double, right? Because it contains all of the power. You just compute. It's only the ones that are coming at that are being the non-zero orders that you need to double because they're the ones that you're omitting from the calculation essentially. Yeah.
Thank you.
And again, suppose I had made a mistake. Okay, so suppose I had incorrectly doubled the reflectance of the m is equal to 0 order. That would have shown up in my results, right? Those tallies would not have been equal to the total flux. So I would have caught it right there, right? So that's another reason why we did this test, right? Because that test verifies that we have set up these calculations correctly. So one of the key takeaway messages here is when you're setting up these calculations, right, do these checks as a way to convince yourself that you're doing the calculation correctly, okay? Because otherwise you could say, take this calculation, extend it to inverse design, do a lot of interesting things, but you realize, oh, I'm not computing the actual diffraction efficiency correctly, right? Because the resolution was too low or the PML was too thin, or I misplaced my monitor or something, right? So this should be the first thing you do before you go on to more complicated calculations. Okay, this is kind of an important message for this tutorial. Yes?
How much error is introduced by this angle discrepancy that you mentioned?
The question was, how much error is introduced by the off-normal incidence? That's actually a very good question. So in my investigations, what I've noticed is that for when you're coming in an off-normal incidence, there seems to be more error in the reflected orders than in the transmitted orders. Okay, and when you're doing this test to validate the tally against the total Poynting flux, I needed to go to these large resolutions to be able to reduce that error, particularly for the off-normal angle for the reflected orders. Okay, so that's something, yeah. I think that has to do with, well, I mean, it might be problem dependent. So specific to this problem, I don't know how generalizable it is, but it's something that I did notice when I was setting up these calculations. Okay, if there are no questions, let's go on to a more complicated structure, which is these 2D triangular lattice. Okay, so suppose now I want to go to something that involves a 2D lattice that's shown here in this schematic. This actually is a square lattice, but suppose I want to use a triangular lattice, okay, which I show here on the left. Okay, so this is a triangular lattice. The unit cell for this triangular lattice would be a triangle, okay, as you can see here. And the lattice vectors A1 and A2 represent for this unit cell what would be a way to define the actual unit cell. But the problem is it's a triangular lattice, and so the unit cell is also a triangle. But Meep only supports currently, anyways, a rectilinear cell, right? So the question becomes, how can I actually model a triangular lattice using a rectilinear cell? And the answer to that is you need to use a supercell. Okay, so that's shown in this figure. So this supercell, you can see this actually has a different set of lattice vectors denoted by A1 prime and A2 prime, okay, which are not the same as A1 and A2. And because of this mismatch, this supercell is going to have additional diffraction orders, which are purely artificial. Okay, they're only an artifact of the representation of this supercell. And so that's something that we need to be careful about in the actual mode decomposition, because we need to be able to distinguish what are the actual real diffraction orders from the triangular lattice versus the ones that are artificial from the actual numerical representation using this supercell. Okay, so just a quick review of the relationship between a direct lattice and a reciprocal lattice. Okay, you might have remembered this from your class in solid state physics. So for a triangular lattice, for this unit cell with these lattice vectors A1 and A2, so in this case, I have the period is, say, lambda, the spacing between any two lattice points. You can generate a set of reciprocal lattice vectors. There's a formula to do so. Okay, so the reciprocal lattice of a triangular lattice is also a triangular lattice. And so you can define any in-plane wave vector as some linear combination of B1 and B2, your reciprocal lattice vectors, okay, in the representation of the unit cell. But now suppose I have a supercell, okay, that's represented by A1 prime and A2 prime, okay. Its reciprocal lattice vectors are B1 prime and B2 prime, and that also has a different set of in-plane supercell wave vectors denoted by N1 and N2, okay. Now the question becomes, when the supercell wave vector is equivalent to the actual wave vector, what's the condition that relates the n's to the m's, okay? And you can go through the math and you find that you end up at this very simple relationship between, if you want to compute the diffraction orders specified by M1 and M2, these are the actual orders that you would need to compute using the supercell. You get N1 and N2. Okay, so again, just to review, you want to model a 2D triangular lattice in Meep. You have to represent that using the supercell, but then you want to compute the diffraction orders of the actual unit cell, which are specified by M1 and M2. Okay, those are the integers that describe this linear combination of the reciprocal lattice vectors or the actual unit cell. To convert those diffraction orders into the orders of the supercell, you need to use this formula, okay, which relates the wave vectors of the supercell to those of the wave vectors of the actual unit cell. And these ends are the quantities that you're going to pass to this diffracted plane wave object when you're doing the actual mode decomposition. That's it. Okay, that's really the only thing that you need to be on the lookout for. And as we'll see, the fake or the artificial diffraction orders, the ones that are purely an artifact of the supercell, they actually carry no power, okay, because they're artificial. And we'll actually see that in the calculation. So in the limit, as the grid resolution goes to infinity, as the system approaches a continuum, the power of those artificial diffraction orders will go to 0. Okay, whereas the ones that are real, those will be non-zero. Okay, so let me turn to the code and show you what that looks like. This actually is an example that already exists in the tutorial, so you can look that up already. Okay, so let me show you the code. Okay, so this example actually is a unit test that is already checked into the repo that does this exact calculation for this 2D triangular lattice and just verifies once again that the total reflectance of the reflected orders and the transmittance of the transmitted orders is equal to 1 for the case of a triangular lattice and an off-normal incident plane wave. Okay, so to set this up, it's a very simple structure. Okay, so in this case, our structure. So this by the way is as I mentioned, is a Meep unit test in test mode decomposition.py in the Meep tests subdirectory. And there's a description here of what this test actually does. So what it's going to do is it's going to compute for an incident plane wave at, in this case, 34.6 degrees, it's just chosen arbitrarily, the total transmitted and reflected orders and make sure that their sum is equal to 1, okay? And it does so using this supercell. So the supercell consists of these 5 cylinders, okay? Which if you recall, they correspond to the locations of the rods. In this case, I have just cylinders, glass cylinders sitting on top of a glass substrate. Okay, here's our substrate. And on top of it are these cylindrical rods. This is, by the way, this is a 3-dimensional calculation, not a 2D as the 1D grading was, just so you remember. So it's a little bit of a bigger calculation, but it's still fairly small and compact. We're going to do, in this case, we're not going to do any, reference run to compute the power in the source. We're just going to compute the power in the reflected orders and just make sure that they equal to their sum is equal to the total Poynting flux. So we do the same way. So we have our simulation object. We add in our 2. I'm sorry. Actually, we do a reference run, as you can see here. So here in this case, yeah, we're going to do a reference run with just the default material of the glass and just the source, where we compute the input power. Same way as we did before for the 1D grading, store the result in these 2 variables, set up our substrate and our grating, and then add our 2 reflection and transmittance monitors. So here they are. And then we're going to do a loop, okay? And this is the important part of this tutorial. We're going to do a loop over these diffraction orders and verify whether they're real or not. Okay, so this is the key part in this script. So we're going to do a loop over, in this case, the -5 to +5 diffraction orders. We're going to take those, so we're going to convert these diffraction orders into the actual orders of the unit cell using that formula that I showed you. And then we can verify whether it's a actual propagating mode by verifying whether the wave vector is real. If it is real, that means it is a propagating mode. And we have to compute the mode coefficients for the two polarizations. So remember what I said in 2D, for a 2D grating, if you're coming in at if you have a linearly polarized source, the output is both polarizations, right? So you have to compute those separately. So that's why we have to compute the S polarization and also the P polarization separately. Okay, so additional calls to this get eigenmode coefficients routine. Okay, we compute the reflectance. And then we're going to just do the sum. We're going to keep a running tally of all the reflected orders and store them in this R sum value. And then we're going to do the same thing for the transmitted modes, okay, and keep a tally. And then at the very end, we're going to just verify the same thing that we verified before. The total reflectance is equal to the total reflected Poynting flux and also transmitted, and their sum is equal to 1. That's it. So let me just show you the output. This is the last thing I'm going to show for this tutorial. Okay, so here's the output from running that actual test. Okay, so you can see it's using MPI and 2 processes. We're coming in at 30, so it's only a single run, 34.6 degrees incident plane wave. We do a reference calculation with just the default material to compute the incident power of the source. And then we put in our actual structure. We create this supercell with these 5 blocks and a substrate underneath them. Sorry, 5 cylinders and a substrate underneath them. We do our time stepping, and at the end, we loop over all of the reflected orders and the transmitted orders, and one by one, we compute their values. So you can see here, it shows you whether it's a supercell reflected order or a unit cell. So you can see the ones for the supercell, they have negligible power, as they should, right? And if you increase the resolution, right, even higher, these should converge to 0 because they're artificial orders, as I mentioned already. The ones for the unit cell, though, they should have some non-zero order, and you'll see this clearly in the output. So again, this shows you the reflected orders as well as the transmitted orders, okay? And then at the very end, it shows you their totals, and you can see they're very good. So about 17% of the input power is reflected and 83% is transmitted, and their sum is roughly 1, as they should be. Okay, that's it for this tutorial. I'm going to stop and take any questions, or if anyone has any questions for the 1D gradient, we can talk about those as well. Thanks, Stephen. Okay, yes. Spherical wavefronts. That's an interesting question. If you have a point source, that can generate a spherical wavefront. So
Maybe it's like a mode decomposition with spherical waves.
I see.
So suppose you decompose the scattered field into spherical waves.
That's an interesting question. In principle, I guess we could support that. We don't right now. Right now, we support localized waveguide modes. And the backend for that is using MPP as a mode solver. And then there's this diffracted plane wave, which is the non-localized. But yeah, that's certainly a feature that we can add.
Basically, you'd have to implement it yourself right now.
Yes.
It's just another mode overlap.
Yeah. So as Stephen said, we can implement this ourselves. It's just another mode overlap integral. You just compute the spherical wavefronts manually, and then compute the overlap integral with the DFT fields from the DFT monitor. Okay, one question actually I want to discuss is, there are other ways of computing diffraction efficiencies using other numerical methods. So a popular one is known as RCWA, and the package that's widely used is called S4. So that's a frequency domain solver that's very efficient for these kinds of calculations because it exploits the fact that they have these constant cross sections, right? So whereas in FDTD, you have to do a volume discretization using these voxels, right? So the entire computational cell has to be modeled using potentially a large number of voxels. In RCWA, you just model the actual constant cross sections, which is much faster for these kinds of problems. Where I think FTTD and MEEP are useful are for things like anisotropic materials, okay? So where you're, where you have an epsilon, which is an anisotropic tensor with non-zero off-diagonal terms. So these are, you could find these in various like lenses for lensing, like a Pancharatham Berry phase lens, I think they're called. FTTD is also useful if you have metallic structures. So suppose you have a metal conformal layer that goes on top. RCWA has some challenges around convergence in those cases because you need to typically have a large number of Fourier orders. The fields have a lot of like discontinuities, for example, that could present some obstacles. In FTTD, you just keep cranking up the resolution. In principle, you can brute force your way to a result. But I think the more compelling reason to use MEEP for this is actually inverse design, which is something you'll hear about later. So to take this calculation and to set it up as an inverse design problem, that could enable some very interesting kind of design applications. And that's something that, and you could do it over a broad bandwidth in a single simulation. So using robust optimization and so on that you'll hear about later on. So I think that's where the value of doing these kinds of calculations in MEEP can be really exploited.